But yeah, we should figure that out sometime soon. You can email me, you know, if you have an idea. So we have talked about quotient spaces a couple days now, right? And so I'm trying to apply it a little bit. And this is section 4 on so-called homogeneous spaces. So he starts by, and of course I'm in Topology by Yannick again, right? And he starts by defining topological group, right? And I mentioned to you guys last time, we looked at the matrix group GLNR and GLNC a little bit, talked about their connectedness properties and stuff like that, remember? Okay, so here's his definition, homogeneous space. If H is a subgroup of G, a topological group, the quotient space G mod H is called a homogeneous space. So what's the so he says, okay, the quotient here is what? What's the equivalence that's being used here? You know, A is equivalent to B in G if and only if what? Yeah, AH equals to BH, if you like, right? Which, of course, we know interchangeable with what? B inverse, what is it? B inverse A is an element of H, yeah? So this is the equivalence. Homogeneous space. Why is it called a homogeneous space? The group action on it is transitive, you say. Let's see if we can come up with an example of this. Let's see here. Let's be really, really kind of stupid. A stupid example, maybe. A silly example. What if we let G equal to, say, R3, right, with respect to vector addition? Then what would a good subgroup H equals to R2? How about H equals to the span of 0, 0, 1, right? Then what are we looking at? What's G mod H? We can look at it as A comma B comma 0 plus H, right? And it's pretty clear that that's isomorphic to, homeomorphic, in fact, to R2. I mean, the picture that I think of in this is something like, you know, so what's a typical coset? It's something like a vertical line, right? And we can identify that coset with its intersection with the whatchamacallit here, xy plane, right? So you said it gives us a transitive group action. Transitive G action on the quotient, huh? So what would that look like here? Oh, okay. Yeah, hold that thought, just a second here. So if we want to move from this coset to a different one, say this one, I'll call that, we want to label this one C? Oh, CD0 plus H. However, so you're going to tell me how to go from one to the other that makes it transitive?
Well, I mean, you can go from this point to another point by the point.
Okay, so
If it's a G action, then you just this
translation by what? Yeah.
by a vector.
So we just add, what do we add? We add C minus A, B minus, D minus B, right? And whatever you want, really. But you could put 0 there. We could put anything there. It wouldn't matter. That would shift this guy over to that guy, which shows you that. What does that show us? That shows us that the induced action of the big group, additive R3, acts transitively on the cosets here. Okay.
The other thing is like the orbit of that action of
The orbit of the G action is the whole. Yeah, let's see here. So we could say G dot, like anything, A, B, 0 plus H, right, is equal to this. That would be transitive. You take the orbit of any point, just like that. Now, we haven't defined orbit yet, but we're about to, okay? I mean, that may or may not be, you may not remember that from abstract, I don't know how much you guys remember, but oh man, it's bright. Golly. So I like his example here. He discusses what is it. He says, think of some mathematical object A and X somehow associated with X in a structure, for instance, a given subset of X, or perhaps a function from X to the complexes. Whatever, something that can be transformed by a group into a similar object, all right? Some object, you have some way of a group acting on it, then you can talk about the orbit of that object under the group, and you can talk about a subgroup of the group which fixes that object. And he says the set H of elements that transform A into itself as a subgroup of G, the so-called homogeneous space of G mod H can be considered in a natural way to be the space of all positions that A can assume under the transformation of elements by G. Let me write that out. He says H equal to G and G. such that GA equals to A can be considered still butchering the sentence, I'm sorry. God, man, that's bright. And the homogeneous space G mod H, okay, can be can be considered in a natural way all right, to be the space of all positions that A can assume under transformations by elements of G. All right, so in order to make sense of this thing I just wrote, we have to think about some object and some group, right, that acts on that object, and then think about a subgroup of the group which fixes the object in order to form the homogeneous space and to make sense of this paragraph, right? His example is as follows. He says, look at G. I want to unwrap this example. G is the orthogonal group of order n plus k, right? And X is equal to Rk cross Rn. And this subset of X that he wants to fix, a subset of X is, let's see here, Rk cross 0, all right? So the question is, what kind of orthogonal matrices fix A? First of all, do you guys remember what orthogonal matrices are? You know what I'm talking about? Nope, okay. So remember, this is equal to, let's say, R in Rn by n plus k by n plus k. So n plus k by n plus k by n plus k matrices such that, oh, excuse me, that's the wrong way. This is not a matrix group in the current context. It's a what? I mean, you could look at it. You can either look at it as a matrix group or a group of transformations. Let's look at it as a group of transformations. As a group of transformations for the moment, it is easier for me to write it this way. It's a transformation T going from Rn plus k to Rn plus k. What makes it such that what? Well, how about this? T of x dot y equal to T of x dot T of y. Preserving Euclidean distance would be isometries, I think. And that also allows, if you're preserving distance between points, that also allows affine transformations, the rigid motions. Euclidean inner product. Well, there of course is an interplay between all these ideas, right? Like, what's that? Equal distance. What are we talking about?
Preserved distance transformation.
Which transformations are we talking about? Preserves distance. Oh, okay, yes. Sure. Oh, I got you. Distance from the origin. That's equivalent to this. Right. Because if you use the Euclidean norm, right, because this becomes the, this doesn't even make sense, what I've written at the moment, right? Does this even make sense? Not really. Nope. There we go. Now, okay, so, because, I mean, otherwise it's come on, I can't feed a scalar to a transformation. But anyway, just, I don't want to get all back into all this, but this, I'm assuming this is linear. All right, a linear map which preserves the dot product. That means, among other things, that, like you guys just told me, the distance, the length of x is equal to the length of t of x for all x, right? Et cetera. And if you look at, so then the question is like, what's the corresponding matrix group, right? That would be a group of n plus k by n plus k matrices, which appear as the standard matrix of these transformations. So this corresponds uniquely to like, I don't really have a different notation for it, honestly. I'll call it matrix. And I think these are just identified, right? That would be like R in Rn plus k by n plus k, such that R transpose R equals to the identity, right? My apologies if when you watch this later you can't see part of what I'm writing, because we are going between vastly different brightnesses on the board right now, and you guys are fine with that because the human eye easily detects the difference between like 10,000 times bright and dark, but technology, not quite so much. So my suspicion is part of what I'm writing can't be seen. Yeah. Oh, okay. Well, I'll try to put a shadow on there. Okay, anyway. Yes. The orthogonal group, right? And so certainly this is a subset of Rk by Rn, right? And then you can ask what of these orthogonal matrices fix A, right? Like if we want to send A to A, if we want, T of A to be a subset of A again, then he points out that the standard matrix of T basically should look like what? It should look like something like this. It should be a block matrix like that because, and how big is M? I mean, this is the n component 0, right? So we're talking about this being like a k by k, right? And this over here would be n by n. In order for that standard matrix to be in O n plus k, that means that the m and the n respectively must themselves be orthogonal. So if you just sort through this condition here, right? If you have m0, 0n transpose m0, 0n equal to the identity matrix, right? Because we're assuming that we're where? This is all happening inside orthogonal n plus k by n plus k matrices, right? And the block matrix thing, that's just plain, do you guys understand where that's coming from? I mean, if I fix the Rk subspace, I have to have a block matrix like that, otherwise I wouldn't fix, I have to have this in order to send these kind of vectors to those kind of vectors again, right? If these were non-zero, that would mean that Rk was moving to some of this stuff. And if this was non-zero, that would mean that some of this stuff was moving to that. Anyway, so what do we got? See, this is just M transpose M, 0, 0, N transpose N, when you do the block multiplication and the transposition, because when you have a matrix like this and you block, do you agree? Disagree? Anyway, so what does that mean? That means M transpose M is equal to IK, N transpose N is equal to IN, which is to say, of course, that M is itself an orthogonal. K and N is in ON. So, in other words, H is equal to OK cross ON. I mean, I guess I might write it's the matrix direct sum of those two, right? And that is a subgroup, right? That's a subgroup of ON plus K, right? So this is everything you need to try to interpret this paragraph of text, right? I mean, what's our space? We're looking at our K cross, or, basically our N plus K space. We're fixing the first K coordinates, right? Sending those to themselves. And then what? He says that the homogeneous space G mod H can be considered in a natural way the space of all possible positions that A can assume under the transformations by G. So what's that look like here? What does G mod H look like? So we're doing what? ON plus K mod ON plus OK, yeah? Or excuse me, other way around, right? OK plus ON is what I want. So that's the homogeneous space, right? Was that identified with? Space of all positions A can assume. What's that here? What does that mean? Well, what he says is that this ON plus K mod OK cross ON is the so-called Grassmannian manifold of k-dimensional subspaces of Rn plus K. Of, what does he say? Of k-dimensional subspaces of Rn plus K. He says, and a particular case that he's interested in, right? Particular case, he says in the case K equals to 1, we look at O n plus 1 mod O1, and I'm going to keep using plus circle if you guys don't mind. He uses cross here. On is so-called R, RPN. So straight lines through origin. Does this make sense? Oh, is my mic working? La la la. Okay. I mean, I struggle with this sort of, prose. A is the line. Oh, okay, can we look at this geometrically? Like where we can do it more, I mean, can we ever view this geometrically? Is there any hope? I mean, this is a group of matrices, mod another group of matrices, and then we're identifying it with something that's relatively concrete. I mean, is there really any hope for me going, oh, I see what that is. Oh, well, now I know what that is. Or is this really just a construction of this in terms of that? So you want to look at X is equal like R cross R? Like that? Oh, R cross Rn? And A equals to R cross the 0? Oh, this is a line. Does that make sense to you guys, why that's a line? Okay. And then what?
And then if we use the G, the orthogonal transformation, A will become another line.
So then GA could be any line.
But it has to be through origin because orthogonal transformation has to fix the origin.
Actually, this is very helpful, King. So here's a very stupid picture, but so this is like, wait a minute. A is like X, right? Like it starts with the first coordinate, right? This is like A. And then by rotating that in however many dimensions you got, right? You can move A to another line, right? Oh. Huh. That actually makes a lot of sense. So this would be something like where G is, What's that? Oh, yeah, I meant an element of the yeah, you got me. Little g is an element, thank you. Sorry, what was messing with me is that I was thinking that A is fixed. I was thinking A is fixed, so how can I get off the x-axis? But what's wrong with my thinking? A is only fixed by what? H, right? That subgroup of the total group we're looking at. things that are not in the, things that are not in the subgroup move A. Everything that fixes A is in H. Things that are not in H move A, right? And they can move A anywhere. Yeah, I think that's the next section. The stabilizer and the orbit's the next section. But I'm just trying to appreciate this prose he has in that paragraph, because when I read it, it sounds reasonable, but then I try to really think through it, and do I really understand it? Maybe I do. So that makes sense, right? The homogeneous space, G mod H, can be considered in a natural way to be the space of all positions that A can assume by the transformations of G. So what's cool about this, right? I mean, you can visualize that, right? You can kind of start to visualize it. Real projective space is a space, it's a quotient space where our equivalence class is lines through the origin. So like any pair of points which is on the same line through the origin is considered to be equivalent. This is real projective space. We'll look at that separately here in a couple minutes, okay? I'm going to go to the other book in a minute because I think it's helpful to focus in on that. It's an important example. But what's neat about this is it just as well constructs a space where if you're working in, you work in 4 dimensions, right? You could work in 4 dimensions and you could let the equivalence classes be, planes through the origin, so that your 4-dimensional space gets squashed into a 2-dimensional space where each point in that 2-dimensional space represents a plane through the origin, right? Or you could look at the 4-dimensional space and look at all 3-dimensional spaces through the origin. And that would make a new space of 3-dimensional slices of the 4-dimensional space. This general idea goes to form what are called Grassmannian manifolds of k-dimensional subspaces of Rn plus k. And he mentions that these are important in the study of vector bundles because there's something like this topological group has to do with how we tie together fibers on a vector bundle. That's what he talks about. But that's past what we're doing in here. But these Grassmannian manifolds are important for other things. All right, so I'm going to try to forge ahead in here, and then I'll come back to the real projective spaces after that. So. All right. I think he does about as good a job as anybody does in terms of explaining what on earth these Klein-Bottle pictures mean. I don't think I'll be able to do that justice to that in class, but I would just encourage you to read it. It's really quite an effort he makes to really explain the geometry of the Klein-Bottle. So I'll see if I can say something in here, but I'm not overly optimistic about my ability to communicate it on the board. But let's see here. So the next thing up here. Oh, I've forgotten. Side comment, small comment. This quotient, this homogeneous space, when is it Hausdorff? Closed. And that's not closed in the sense of being a subgroup. That's closed in the topological sense. So, yeah, while I'm at it, what's a Lie group? Okay? What's a Lie group? Is this a manifold? With smooth group operations. So that's, now you could say, well, what does this word mean? What does manifold mean, right? And someday we have less, when we have less on our plates, I'll come back to that, okay? I don't want to do that today. Enough for today, all right, in terms of that kind of thing. Some other day we'll do that. But the thing is, part of being a manifold is that it has to be Hausdorff, right? So like Hausdorff topology. So if you wanted to take a Lie group, if G was a Lie group, right? And you wanted, if you wanted G mod H, if you wanted G mod H to be a manifold in its own right, what would you need about H? You would want H to be a closed in the topological sense subgroup, right? A closed. So if this is Hausdorff, right? Provided H closed, and so just to give you, I mean, what's an example of a Lie group? In fact, I've already shown you examples of Lie groups, like GLN. GLNR is a Lie group in a pretty easy way, right? And what's a closed subgroup of GLNR? Right, SLNR. This would be a closed subgroup of GLNR. And there's a theorem which says that if you have a Lie group and you quotient by a topologically closed subgroup, sub-Lie group of it, which this is, then the resulting object is a manifold. And part of that is that it's a Hausdorff topological space. So this is actually a manifold. It's more than that, right? Because SLN is also what? It's also the kernel of the determinate map and is hence a normal subgroup. So in fact, this is not just a manifold, it's also, in fact, a Lie group because H is normal. And so the quotient space is itself a Lie group. It's a group, and it can be shown that it's in fact smooth with respect to the operations. What's the dimension of the manifold, though? What's the dimension of GLN? If you had an open subset of R3, what's the dimension of that set? It's the same, right? An open subset of R2 is two-dimensional. An open subset of Rn is n-dimensional. An open subset of Rn by n matrices is n squared dimensional. So this is n squared dimensional. What's the dimension of SLN? Ooh, now that's a little bit harder right off the top of my head, but remember in abstract algebra? Somebody here was in abstract, right? Nobody? Dang it. I've been misbehaving in abstract lately, making them calculate the dimension of Lie algebras for Lie groups, among other things. And you can show that the Lie algebra of this little SLN is equal to essentially n by n matrices such that the trace of A is equal to 0. It's not obvious why that's true, but it is. Well, I can tell you why. It's because the exponential map gives you a coordinate map from the Lie algebra to the Lie group, like generally speaking, exponential. And this is the matrix exponential. It gives you a mapping from the Lie algebra to the Lie group. In this case, we're talking SL and R. I am way off track, guys. Sorry, guys. SL and R. I will get back on track eventually. It's just turned out to be much more involved to explain why I'm saying what I'm saying than I thought it was. I'm so sorry. I will get to the point here eventually. So, if you look at a path of matrices in here, it turns out that the determinant being 1 and the fact that the determinant of the exponential of A is equal to the exponential of the trace of A, by the way, means that if the determinant is 1, it forces the trace to be 0. So trace 0 is the condition that's needed for SLN, little SLN, the Lie algebra of SLN. Getting back to my question, what's the dimension of that space? The dimension of the Lie algebra is the dimension of the Lie group. So trace A is what? I think that it's really just what? It's really just one real equation, isn't it? So we're taking an n squared dimensional backdrop. We're imposing one real equation on it. So what's the dimension of SLN? What'd you say? It is in fact n squared minus 1, yes. So I said that GLN mod SLN is a manifold. There's a theorem in Lie group theory. We learned the following theorem. The dimension of G mod H, guess what it is? It's the dimension of G minus the dimension of H, as it turns out. So this, the reason I'm talking about this at all is, how is the topology on this defined? It's quotient topology, right? So like at the base of manifold theory is topology. We have to understand topology to do anything like all of this really carefully. But the stupid thing that I'm telling you at the moment is this is a what dimensional manifold? What? Well, yeah, one dimensional. And so what have I done? I've shown you a very, very complicated way of constructing the real numbers. GLNR. This is really just isomorphic to R. And so if we go back to our discussion about homogeneous spaces and the paragraph of text I'm struggling to understand, does it make sense? If we think about SLNR and we think about moving it, think about moving it throughout GLNR, right? This would suggest that the position, that there's the homogeneous space can be considered in a natural way in the space of all positions that A can assume. Can you write any invertible matrix in terms of a special linear matrix? Like if you take, how would you do it? If A is in GLNR, can you rewrite A as equal to something times B, where B is in SLNR? Is that how it works? I don't know.
What happens to the determinant of the matrix being multiplied by the scalar?
That's not a scalar, though. G is also in here. I'm sorry, I've gotten way, way off track. I'm so sorry, guys. I should go on. Oh, what's wrong with me? B. So well, that's kind of embarrassing. You're, you're suggesting for for A and GLNR, if I want to move.
If you want to move to something in the special Lie group, I don't know what happens to the determinant of the matrix when you multiply by.
I feel like I'm missing something in this discussion. I'm sorry. There's something that's too trivial about what we're doing at the moment. Let me. His next example is much better. Let's look at it. Matrix with same determinant will be sent to same coset. If I have the determinant of A equal to the determinant of B, then the determinant of, you say AB inverse or B inverse A? B inverse A, I mean whatever, is 1. And what's that say? So ASL NR is equal to BSLN. Why didn't I call that H? AH, equal to B. Setting H equal to. What's that? Huh. Ah. The coset is isomorphic to R. I suppose that the I think the homeomorphism here is just what it's AH maps to what? Right, determinant of A. So this gives me the psi is from G mod H to R. Oh yeah, you're right. You're right. It's a one-dimensional manifold. I jumped the gun. It's not R. It's what? It's non-zero reals, isn't it? And that makes sense. Why? Oh, good connection with last class. Disconnected gives what kind of quotient? Did we have that? Was that a? I mean, we had path connected quotient. I mean, what was preserved under quotients? What was it? It's been so long, I've forgotten. So is SLN? Well, anyway, I connected and path connected. But it makes sense that the quotient here would be disconnected, and that's what R with 0. This is, you understand what this is? This is minus infinity 0 union 0 to infinity, right? Like, here's how I'm visualizing that. If you think about all of GLN, right? There's two pieces. There's the plus determinant and there's the minus determinant, right? And so somewhere in the plus determinant, there is H. I don't know if that's even, I'm not sure that does it justice. I mean, it's it's of one dimension less than, maybe that's the right kind of picture. It's one dimension less than GLN itself, right? SLN is like n squared minus one dimensional, whereas GLN is n squared dimensional. So inside this, in this quotient, we're identifying all of SLN as one point, right? So it makes sense that it's still disconnected because you're just squashing one thing and one of the things that's being separated, right? It seems like if you had a disconnected set and you quotiented, if you did a quotient by something, wouldn't it connect it if you did this? If you quotiented by something that was connecting the separation, wouldn't that in the quotient become connected? I think it would, right? I mean, if my intuition is worth anything, that's debatable. Okay. Sorry. So thank you for the comment. Let me try to forge. Don't look that way. All right. So as you guys were trying to get me to talk about orbit, what's an orbit? If X is a G space, what's that mean? So that just means that X is a set on which the group G acts. And because this is topology, we're assuming that this is a continuous group action, that's a topological group, all right? And so that's the orbit. He gives us axioms. What's the axiom for the group operation, group action? What does it take for it to be a G space? A couple things, right? It means that 1 times X is equal to X for 1 in G, right? For 1 being the identity in G. And also, if we have G1, G2, X, we get G1, G2X. In other words, if I first multiply G1 and G2 in the group and then let that act on the point X, it's the same as if I let G2 act on X first and then act on that, like that. So the difference between the left-hand side and the right-hand side of what I just wrote on the board is that there's one group multiplication followed by one action of that group element on the space X. In contrast, on the right, we let the group element G2 act on X, move it, and then we let G1 act on that point which has been moved in the space X. Okay, so those give us the same output. Anyway, this is axiom 1 and axiom 2 for a group action. And again, we're assuming that this, as he says, G is a topological group. So that's an orbit. And definition, orbit space, if X is G space, then the set of orbits endowed with quotient topology is called the orbit space. And we denote that by X mod G. Now, notice that this differs from the notation that has been used, because I'm not saying that G is a subset of X. All right, X could be like a set of 3 vectors. G could be a matrix group or something, But what's the equivalence that we're using? So the example he gives looks like the 2-sphere. subset of R3, all right? So like here's the z-axis, right? And it's the unit two-sphere. So like this point would be 0, 0, 1, and the south pole would be like 0, 0, -1. Okay? And then what group does he let act on this space? So let's see here how to say this. Rotations about z-axis. So if you look at rotations, what would be the matrix of a rotation about the z-axis? Something like this, right? Yeah, your cosine theta, you got your like sine theta, minus sine theta, cosine theta, something like this, right? If I let this kind of matrix rotate points in R3, that's a rotation around the z-axis, right? And is it clear? I mean, it should be clear to you that if we look at G acting on S2, what happens? Let's say if P is an element of S2, then RP is an element of S2, right? It's closed. If you look at rotations of the z-axis of the two-sphere, we're still on the two-sphere, right? Right, and then that's the next question. What are the orbits then? Yeah, let's see, words. Latitude or longitude? You don't know which one's which? The orbits are then parallels of latitude and the two poles. I paid good money for that book, right? So, yeah, so this is, for example, an orbit, something like that. Right? If I start out with this point, RP could be, anywhere around that circle, but Z is fixed, right? So, yeah, the orbits are circles, right? Or, of course, there are two special orbits, right? This guy and that guy, just the north and south pole. And so he says what we're dealing with here then is x is S2, all right? So S2 quotient G in the sense of this definition of orbit space, right? This is homeomorphic to, he says, -1 to 1. Which makes a lot of sense, right? I mean, but we can prove this. It's not just a picture. There's a specific proof, and here's the specific proof. And this will tie back into what we did last time. He says, consider the continuous map pi3, which is a mapping from S2 to -1, 1. Pi3 is what? So like pi3 of x, y, z equal to? Yeah, just z, right? He says, since pi3 is constant on each orbit, pi3 of, let's see here,